Welcome to this lesson on surface area of composite figures, and we will also go over application problems in this lesson. A composite figure is made of two or more 3D shapes. To find the surface area of composite figures, you can either add or subtract. Depending on what the shape looks like, it's usually adding the surface area of the different shapes, and then you'll get the total surface area. One thing you don't want to do is count the bases where the two shapes are joined or connected. That's where you're going to be subtracting occasionally. Okay, so here we have a snow cone and we want to find the surface area. So the first thing you want to do is identify the two shapes. So in this case we have, it looks like a sphere on top, but not a whole sphere. It's actually called a hemisphere, which is just half a sphere. And then we have, of course, a cone on the bottom. But what you don't want to count is this space here where they're joined, because that's not part of the surface, part of the outside that you could touch. We have the cone on top, the cone on bottom and the sphere on top, but you can't actually touch that middle part. So that's not going to be part of the total surface area. All right. So now what we want to do is we want to find the area of the sphere first, and then we're just going to cut it in half. So if you think about a sphere doesn't normally have a base. So we can just use the normal sphere formula, which is 4 pi r squared. And then we're just going to cut that in half. So we really don't have to worry about that base because a sphere doesn't actually have a base. And then for the cone, a cone does have a base normally when we find the surface area. So we want to leave that part out. So if you think about the formula for a cone, I'm just going to write that formula out. So pi RL plus pi r squared. Now the base of a cone is that circle, that pi r squared part. So we don't want to count that part. So I'm just going to X this part out. We just want this section here. All right, so let's fill in our units. So the radius is 2 for both. All right, so for my hemisphere, that's going to be 4 times 4 on top, that's 16 pi, divided by 2, that's 8 pi. Now for my cone, be careful because it calls for the lateral area, the lateral length, which is also the slant height. We've been calling it that too. It can also be that L because it's just this length of this lateral side here. But we just have the normal height of that cone. We don't need that. So what I can do is I can take this triangle here. It's a right triangle. Let me draw it a little better. So this is 4, this is 2, and we want to find this. And then we can use Pythagorean theorem to do that. So 2 squared plus 4 squared equals x squared. So let's see, that would be 4 plus 16, that would be 20 equals x squared. Take the square root of that, and that is 4.5 here. So pi to 4.5. All right, 4.5 times 2, that's 9 pi. Now, remember we're finding the total, so lastly I want to add these together, so that would be 17 pi inches squared, or about 53.4 inches squared. All right, let's do the examples. All right, so find the surface area of the composite figure. So we have a pyramid here. We don't want to count the base of the pyramid. And then we have that prism. So let's do the pyramid first. And I'm going to use nets to do this. So I'm just going to take apart those shapes. So here is that larger triangle. And then I'm going to use the skinnier triangle. All right. So this would be 10 because this is 10. All right, I know this is 11, on both. This is going to be 4 here. 4, 4. All right, next let's draw the boxes, the rectangles for my prism. Again, we don't want to count this one because that's where they join. So we have this larger 10 by 4 one. That would be this. Then we have this guy. We actually have 2 of those. 6 by 4s. I'm going to put times 2. Also on these, we have 2 of both of these because there's 4 triangles. Just one of these though, that bottom, because we remember we don't want to count the top. All right. Then we have these here, this 10 by 6 times 2. So let's find the area of all these shapes and then we're going to add them all up. So of course, this is going to be 60, 10 times 6, this will be 24, this will be 40. Now on the triangles, we're going to have to use Pythagorean theorem to find that height. So I'm just going to redraw this down here. So this would be 5 because it's just half of this, and 11. 2 and 2. Go ahead and pause the video now and find the height of both of those. Of course, remember you're using the Pythagorean theorem. Okay, so on that bigger triangle, you should have gotten a height of 9.8. And on that skinnier triangle, you should have gotten a height of 10.8. So why did we need the height? Well, to find the area of the triangle. So remember, area is 1/2 base times height. So for this larger one, it would be 1/2 10 times 9.8. Now I'm running out of space here. Of course, if you need notebook paper, grab notebook paper. That would be 49. Remember, there's 2 of those. And then for the skinnier triangle, 1/2 4 times 10.8. And that gave me 21.6 times 2. All right, so adding it all together, we got a lot going on here. This is one of the more difficult ones. We have 49 plus 49. Okay, check. We have 21.6 plus 21.6, check. We have just that 140. I'm just going to continue on, check. Plus 24 plus 24, check. Plus 60 plus 60, check. That should give me all of the bases that are, or all of the faces that are showing. All right, so grab a calculator, add all those up. And we should have gotten 349.2 millimeters squared. All right. Number 2, we have a cone and we have a cylinder, but we're not counting this part where they're joined together because that's not going to show on the outside. So for the cone, it's going to be similar to that one we did here where we're just counting pi RL, the slant height. So pi 3.59. Remember, this is the slant height. For the cylinder, if we think about the formula for area, surface area of a cylinder, let me write that out. It's 2 pi RH plus 2 pi R squared. So this counts for the 2 circular bases, 2 pi R squared. Remember, pi R squared is area of a circle. But in this particular case, we just want one of those circular bases. We don't want this one. So I'm going to rewrite that formula as just pi R squared. All right, so we have 2 pi 3.5 times 6, that's my height, plus pi 3.5 squared. All right, so I'm going to just use my calculator. So pi times 3.5 times 9. That's going to round up to 99. All All right, 2 times pi times 3.5 times 6. That's about 131.9 plus pi 3.5 squared. And then add those together. That gives you about 170.4. And then one last step, we want to add those two surfaced areas together to get the total for this composite figure, which is about 269.4 yards squared. All right, you can pause the video and complete the practice, and then you can unpause the video when you're done with that, and we will do application problems. Okay, so let's look at application problems. Surface area is used in the real world all the time, so let's see how. So number one, a company is testing 2 different box sizes for a product. They want to know which box uses the least amount of cardboard so they can save on costs. So box number 1 is 8 by 6 by 2. Box number 2 is 7 by 8 by 1. So basically we just need to find the surface area of both, because that would be the cardboard of the box, and see which one has a smaller surface area. So I'm just going to write box number 1, box number 2. Boxes are rectangular prisms. All right, the formula is and remember, it really doesn't matter which you label as length, width, height, as long as you multiply each one by the other. So I'm just going to say 8 times 6 plus 6 times 2 plus 8 times 2. All right, and then I'm going to do the same thing for box number 2. 7 times 8 plus 8 times 1 plus 7 times 1. All right. Let's see, that's 48 plus 12 plus 16. So that would be 152 inches squared. That's 56 plus 8 plus 7. That would be 142 inches squared. We're not done, because remember, you have to actually answer the question, and the question says which box will use the least amount of cardboard. That would be box number 2, because it's 142. So in application problems, always go back, reread the question, and make sure you've actually answered the question. All right, number 2, the radius and height of a cone are doubled. How would this affect the surface area? Prove it. Well, let's just make up a cone. This is going to be the original cone. And remember, the formula for a cone is pi RL plus pi r squared. Now be very careful, because the height that it's talking about is not the same thing as the slant height. Let's see if I can draw a cone here. Okay, so let's say that the cone has a radius of 5 and a slant height of, I'm going to use Pythagorean triples to make this easier on myself, 13. You'll see why in a second. So I need the actual height here. So I'm going to use Pythagorean theorem. That's going to give me a height of 12. All right, so I'm going to find the surface area using these. And that gives me 90 pi. All right, I'm going to switch colors here because I want to be able to differentiate. So this is going to be the bigger, the doubled cone. And you'll see why we had to actually use that height. So it says the height and the radius are doubled. Okay, so I'm going to redraw. Of course, imagine it 2 times as big, but I don't have the space for that. So my radius is now 10, which means my height is 24, because remember it's 12. We doubled it to 24. We need the slant height, though, for the actual formula. Now, of course, there is a formula for cone that has the height in it. If you want to use that, go right ahead. It's just a little more complicated. All right, so Pythagorean theorem. My slant height is going to be 26. So pi 10 26 plus pi 10 squared. Type that in your calculator, and you get 360 pi. So how did this affect the surface area? Well, if we take 360 divided by 90 to see how much bigger it got, that gives us 4. So when we doubled the dimensions, the linear dimensions, the radius and the height, the surface area quadrupled. It got 4 times bigger. All right. All right, number 3. Seth is making paper models of 3D shapes. He has 25 square inches of paper. If he wants to make a model pyramid with a square 3x3 base and a slant height of 10, does he have enough paper? Okay, so let's use the surface area formula for a pyramid. Remember, that's 1/2 or base plus 1/2 perimeter times slant height. So the area of the base, if it's 3x3, that would be 9. The perimeter, 3 plus 3 plus 3 plus 3 would be 12. The slant height was given in the problem, 10. All right, so let's see, that would be 120. Half of that is 60, so 69 inches squared. And he only has 25 square inches of paper, so he definitely does not have enough paper. All right, and the last one, find the surface area of a square pyramid with a 10 by 10 base and a lateral edge length of 12. All right, so we're going to use that same formula from number 3. So here is my 10 by 10. So that would be 100. 10 plus 10 plus 10 plus 10, that would be 40. Now be careful, lateral edge length is not the same thing as slant height. So if you think about, here is your lateral edges. Slant height is here. Lateral edge is here. All right, this is also 10. So what we need to do is find the actual, we don't know if that's 10. We know the bottom is 10. We need to find the actual slant height of this pyramid. So I'm just going to use the Pythagorean theorem. All right, so x squared plus 5 squared equals 12 squared. That's going to give me 10.9. All right, type that in my calculator. And I get 318 feet squared. All right, you can stop the video and complete your practice.